Chapter 21 is about oscillators, and I think the easiest way to get started in oscillators is to think about square wave oscillators. And the easiest one of those is built using a simple inverter. So the 74HC14 is a Schmitt trigger inverter with hysteresis. So I don't know if you remember this from chapter 20, but this is the symbol that we used when we had circuit input with hysteresis. And that means it has a different threshold depending on whether it's going forward or going negative. Let me just refresh your memory on that. Let's go back to figure 20-19, which is a non-inverting Schmitt trigger. And you can see that the hysteresis curve is the one here where you've got the upper and lower trip point, and the output either swings up to VSAT completely or it swings down to minus VSAT. So this symbol here that's generated by the hysteresis curve is the one that we see in the center of the 74HC14 inverter. So what this symbol means is that when the input is going in the positive direction, it has to reach a certain threshold before the output will go low. And then when it's going negative, the threshold has to reach a different point before the output will go back high. So you have an upper and a lower trip point, and if you connect these with an RC network, you will get an exponential increase and decrease from the output to the input. So here's the data sheet from a typical 74HC14. It's a hex inverter, so you'll find that there's 6 in one package, and you can see that here. To look for the thresholds, you go down in the data sheet to the input-output characteristics, and so here we are here. The positive switching threshold is typically, if we have 4.5 volt supply, it's typically 2.5 volts. So on the forward going edge, it'll go low when the input is 2.5 volts, and then the negative switching threshold, when the input is going low, when it goes below 1.6 volts, then the output will go back high again. So on the rising edge, when the input hits 2.5 volts, the output will go low. And when the input goes down to less than 1.6 volts, the output will go back high again. So when we looked at these with inverters in chapter 20, this was known as the upper trip point, and this was known as the lower trip point. And if we tied an RC network from the output back to the input, we could figure out how long it took for it to go from the upper trip point to the lower trip point. The period that it takes to do one cycle would be 2 RC ln, and the ln would be basically the ratio of the two voltages. That would give you the number of tau if you took the natural log of the ratio of the voltages, and then multiplied it by the RC time constant, and then of course 2 times, because it has to go up and then down. So the period then would be 2 times 1,000 for the resistor, times 1 times 10 to the minus 6 farads, times the natural log of this stuff, which is 0.45. That comes out to 893 microseconds, or 1120 hertz. Now I've entered the circuit for the 74HC14 oscillator into Multisim. Here's the output of the inverter. So when this goes high, it starts to charge this capacitor up through this resistor. So it slowly starts to rise up until it becomes a 1 on the input, which results in a 0 on the output. And then the output goes low and it discharges the capacitor. So there's a 180-degree phase change here between input and output. And when the output goes high, there's a time delay for the capacitor voltage to rise. And when it goes low, there's a time delay for it to fall. Let's start the simulation and see what we get. So here we are on, we'll put it on single. And we'll just stop it there. And I'm going to use the oscilloscope cursors here to measure the voltage at different points. So here, right at this point, I can see that the peak value of the capacitor charge is about 2.8 volts, and the minimum value is here, which is about 1.56 volts. So the upper and lower trip points are pretty much what we said they would be from the data sheet. And then the time for one full cycle. So here it goes down and then up, which is one full cycle. That is 837 microseconds, which is very close to what we calculated of 893 microseconds. So let's summarize the operation of the square wave oscillator. So the output goes high, which charges this capacitor up. So we can see the capacitor voltage start to charge, but at some point it reaches the upper trip point on the input. And now it's all considered a 1 on the input, which should result in a 0 on the output. So the output toggles down again, and then the capacitor discharges through that resistor to the low voltage output until it reaches a point where it goes below the lower trip point, and then the cycle repeats. So here's the voltage on the capacitor going high and low, and the output toggles high and low, and it swings up to the most positive voltage and then down to the most negative voltage. So you can think of the gain of the circuit as being infinite, because any change, any delta V on the input between the threshold voltage and the current voltage will result in the output flying off to either the most positive or the most negative rail.